Hi, I am Dr. Sham Sharkar. Welcome to my class. So, my today's discussion is on John Taylor distortion. Okay, because from this portion, one question is very common in any of the competitive exam related to chemistry. For example, IIT JAM, CSIR NET, GATE, SET, etc. Okay, so you will know here John Taylor theorem or John Taylor effect or John Taylor distortion. Sometimes it is not called, and I'll show you smart way or smart techniques for the identification of John Taylor distortion. Which system will show John Taylor distortion and which will not show. So I'll discuss about those things, and next I will discuss all the previous year's problems with explanation, proper explanation for IIT JAM, CSIR, NET, GATE, SET, etc. Okay, so let's start with John Taylor theorem. So John Taylor theorem states that for a nonlinear molecule in an electronically degenerate state, distortion must occur to lower the symmetry of the molecule, to remove degeneracy, and to lower the energy of the system. Okay, so this is the John Taylor theorem, and I'll show you how John Taylor distortion occurs, why occurs. Okay, so now see here I have underlined one sentence, that is electronically degenerate state. So what is electronically degenerate state? So electronically degenerate states are those in which more than one degenerate orbitals are available for a single electron. Then the state is known as electronically degenerate state. For example, if we consider D1 system, so in D1 system you know that electron may reside on any one of the three T2G orbitals, because dxy, dxz, dyz, so three T2G orbitals are available for one electron. So electron can reside any one of them. So this type of state is known as electronically degenerate state. Sometime in many textbook it is written like degenerate electronic state. So that is also correct. This one also correct, electronically degenerate state. Okay, so both are correct, so no need to confuse here. Okay, so now why John Taylor distortion occurs, or how it is happening, how distortion is happening. So let us see. So see here, in electronically degenerate state we know that electrons are asymmetrically distributed in orbitals, and hence they will have more energy. So to minimize that energy, therefore they will try to minimize their energy by lowering overall symmetry of the molecule. For example, if we have octahedral symmetry, then they will lower their symmetry and it will go another symmetry which has less symmetry system. Okay, and this leads to the distortion in molecule, which is known as John Taylor distortion. So sometime in shortcut notation we say that JTD, John Taylor distortion. So why John Taylor distortion occurs? Because of minimization of their energy. And how they minimize their energy? Lowering overall symmetry of the molecule. So this is what you should remember about why and how John Taylor distortion occurs. Now I will show you little later with pictorial diagram how it's splitting further, T2G and EG orbitals further splitting, and they are splitting due to John Taylor distortion. Okay, now how to predict John Taylor distortion. So here see I have shown you three different category of John Taylor distortion. One is strong John Taylor distortion, second one is weak John Taylor distortion, and third one no John Taylor distortion. So which configurations falls in these three category we will see. So see here, when EG orbital is asymmetrical, or sometime it is also somewhere you can see unsymmetrical, or asymmetrical, EG orbital shows strong John Taylor distortion. Okay, now weak. So in case of weak, if T2G orbital is asymmetric, then we will observe weak John Taylor distortion. Okay, and when both EG and T2G are symmetrical, then there will be no John Taylor distortion. So these three things if you remember, you can solve any problem related to identification of John-Taylor distortion in any competitive exam. So these three are the key points for the determination or prediction of John-Taylor distortion. Okay, so strong for, very clearly remember, strong when EG is asymmetrical, weak when T2G is asymmetrical, and no when both T2G and EG are symmetrical. Okay, so now I will show you one by one, starting from D1 to D10, whether which one will fall under this three category. That means which one will show John-Taylor distortion and which are not. So let's see from D1 system. So see, for D1, one or electron is there, it can reside any of the T2G orbital. So here T2G is asymmetric and there is no electron in EG, so EG is symmetric. So T2G asymmetrical and EG symmetrical, that means electronic arrangement in EG orbital is symmetrical and electronic arrangement in T2G is asymmetrical. So it will show weak John-Taylor distortion. Okay. So as I have shown just in the previous that weak John-Taylor distortion occurs when T2G is asymmetrical. So next let's see D2 case. So D2, so see D2 means here also T2G asymmetrical and there is no electron in the EG orbital, so EG asymmetrical. So this one also will show weak John-Taylor distortion. Okay, now let's see in case of D3. So D3, see, three orbitals of T2G are filled with one electron. So here in case of D3, T2G is symmetrical and there is no electron in EG orbital, so EG also symmetrical, so both are symmetrical. That means there will be no John-Taylor distortion. Okay, so D1, D2, D3 you have learned. Now I'll go for D4. So in case of D4, there will be two types of complex. One is high spin, another one is low spin. So depending upon the ligand, we will say which one is high spin and which one is low spin. That I have already talked about in my previous video. So here D4 for high spin. High spin means there will be more number of unpaired electrons. So here you can see T2G3 EG1. D4 configuration T2G3 EG1. So in this case T2G is symmetric but EG is asymmetric as one electron is in EG orbital. So this will show strong John-Taylor distortion because here EG is asymmetrical. So EG asymmetrical means strong John-Taylor distortion. Okay, next see in case of low spin D4. So D4 low spin means all electrons are in the T2G orbital and here you can see that T2G is asymmetric and EG no electrons, so symmetric. So this will show weak John-Taylor distortion. Okay, so D4 with high spin and low spin shows different behavior to the John-Taylor distortion. Okay, now in case of D5, let us see what happening. So D5 high spin, that means all electrons are unpaired and 3 electrons in the T2G and 2 electrons in EG. So both T2G and EG are symmetrical with respect to electronic arrangement, so there will be no John-Taylor distortion in this case. Let's see what's about low spin case. So D5 low spin, see here T2G is asymmetrical and EG symmetrical, so there will be weak John-Taylor distortion. Okay, so this was about D5. Now let us see D6. D6, see from here you can easily say that T2G is asymmetrical, EG symmetrical, so there will be weak John-Taylor distortion. Okay, so what's about low spin D6? See, low spin D6 means T2G symmetric, EG symmetric, so there will be no John-Taylor distortion. Okay, so this is D6. Now let us see D7. So D7, see D7 means T2G 5 EG2. So T2G 5 means this is asymmetrical and EG2 means this is symmetrical. So it will show weak John-Taylor distortion. Okay, now what's about low spin D7? So in case of low spin D7, see T2G6 EG1. So T2G is symmetric but EG is asymmetric. So it will show strong John-Taylor distortion. Okay, so next see D8. So in case of D8, both high spin and low spin complexes will have same electronic arrangement. So that's why I have not shown in separately. Here D8, both in case of high spin and low spin, similar arrangement of electrons will be there. So let us see what is the electronic arrangement in D8. See T2G6 and Eg2. So T2G6 is symmetrical, Eg2 also symmetrical. So both T2G and Eg symmetrical. So there will be no Jahn-Teller distortion in case of D8 high spin and as well as low spin complexes. So no JTD in case of D8. Okay, let us see in case of D9. So D9 also, both high spin and low spin configuration will have similar electronic arrangement. So in case of D9, T2G6, that means symmetric, Eg3, that means asymmetric. So asymmetric Eg means it will show strong Jahn-Teller distortion. Okay, so what's about D10? So in case of D10, here also electronic arrangement is same for both high spin and low spin complexes, and here you can see that in case of T2G, T2G6 and Eg4, so both are symmetric, so there will be no Jahn-Teller distortion at all. So these all were from D1 to D10, which one will show Jahn-Teller distortion, strong and weak, and no Jahn-Teller distortion. So you have to remember all these things in shortcut way, because in exam you will have very less time to think. So if you remember some shortcut way, that will be better for you. Okay, so I'll show you the smart way to predict Jahn-Teller distortion. See, here I have shown similar 3 points like strong, weak and no JTD. So now I will do 2 columns, one is high spin, one is low spin. Okay, now see, I will write some numbers, just like we dial some emergency numbers. So just like that, I will dial 4979 1267 1245 358 110 10 and 368 10. So these all are not only numbers, they correspond to their number of d electrons. So if you remember numbers like these, that means 49 high spin, 79 low spin. These 4 numbers will show strong JTD, strong Jahn-Teller distortion. Okay. Similarly, 1267, 1245. So they will show weak Jahn-Teller distortion, and rest, that means 35810, 36810, they will not show any Jahn-Teller distortion. Okay, so these things you can remember. Also you can do manually also from D1 to D10, just now I have shown. So both way you can predict Jahn-Teller distortion, which one fits for you, which one is, if you think this one is better to do in exam hall, so you can use this one. Otherwise you can do manually from D1 to D10 like that, just now I have shown. Okay, so which one is easier for you, you can follow that one. Okay, so let us see Jahn-Teller distortion with an example. So here I have shown for CuH2O6 2 plus, that means D9 system. Okay, so D9 system will have T2G6 and Eg3 configuration. Now T2G is symmetrical, so we will not consider T2G. See here Eg3. So Eg3, Eg orbitals means we know that Eg contains dx square minus y square and dz square orbital. So Eg3 means it may have either dx square y square 1 dz square 2 configuration, or dx square minus y square 2 dz square 1 configuration. So depending upon these two configuration, there will be 2 different type of distortion. Let us see what are these 2 different types of distortion. So case 1, where dx square minus y square 1 and dz square 2 configuration. See, in this case, 4 ligands along x and y axis will be less screened from the electrostatic attraction of copper 2 plus ions than 2 ligands along the z axis. Okay, so since less screened, so 4 ligands in the xy plane will be drawn more closely to the copper ion compared to the other two ligands on the z axis. So this gives rise to a tetragonal distortion with elongation along the z axis, and this is why this is also known as z out distortion. Okay, so this is z out. Z out means it is both ligands along the z axis are getting elongated. So elongated along the z axis, that's why z out. So bond lengths along the z axis, that means axial to bond lengths, will be longer compared to that of other four equatorial bonds. So this phenomenon is known as z out distortion. Okay, when configuration is d1 x square minus y square and d2 z square. So this type of configuration leads to the z out distortion. Now case 2 is when two electrons are in the dx square minus y square and one electron in dz square. So in this case, just reverse phenomenon will happen. That means four ligands along x and y axis will be more screened from the electrostatic attraction of copper ions compared to that of ligands along z axis. Okay, hence two axial ligands along the z axis will be drawn more closely to the cation than other four ligands along xy plane. So this gives rise to a tetragonal distortion with contraction along z axis, since they are more pulled by the Cu2 plus ions along the z axis. So they will be shortened, bond lengths will be shortened, and this is why this type of phenomenon is known as z in. So this is z in and first one was z out. So if you see diagram of this type of distortion, see this is normal octahedron, and from this if you see z out means elongation along z axis, and z in means shortening of bonds along the z axis. So this is z in and other one is z out, and in middle one is normal octahedral. So if you see the splitting pattern, so this is normal octahedral, and we know that d orbital splits in two energy levels. One is T2g having dxy, dyz, dzx, and Eg having dx square minus y square dz square. Now difference between these two levels is known as delta O. So this separation is known as delta O. Now if you see, I have just said in the definition. So they will be splitting further for the removal of symmetry. That means they will try to lower more energy to get stabilization. So here T2g and Eg orbital further splits to get further stabilization due to Jahn-Teller distortion. So let us see in case of z out and z in how further splitting of T2g and Eg orbital occurs. So here see for T2g, see in case of z out, it is splitting like dyz, dxz having lower energy and xy component is having higher energy. Similarly, in case of dx square y square and dz square, xy component will have a higher energy and z component, that is dz square, will have lower energy, and it is denoted by del 1 del 2. Now see the difference between dxy and dx square minus y square, these two level separation between these two level is denoted by delta O. So delta O here is the separation of energy between dxy and dx square minus y square level. So on the other hand, in case of z in, so T2g splits in the reverse way, and here dyz and dzx, that means z component will have higher energy and xy component will have lower energy. And similarly, Eg orbitals also splits in reverse order compared to z out. So dz square will have higher energy and dx square minus y square will have lower energy. Here also separation between dxy and dx square y square will be denoted by delta O. So delta O is everywhere same. Okay. Now what is the energy order of delta O and small del 1 del 2? So delta O is much greater than small del 1 greater than del 2. Here see in pictorial diagram, so don't confuse, it may not be drawn in the same pattern. So but energy order is always true, that is delta O is much greater than small delta 1 is greater than delta 2. Okay, now let's know what's about static and dynamic John-Taylor distortion. What is static and what is dynamic John-Taylor distortion? So static means, see, when complexes will show measurable differences in bond lengths. So you can measure the differences between types of bond lengths. That means axial and equatorial bond lengths will be different, distinct. So it can be measured. So that's why when complexes shows measurable differences in bond lengths at any condition, like in solid state or liquid state or room temperature or high temperature or low temperature, at any condition when you can measure the differences in the bond lengths of complexes, then this type of distortion is known as static John-Taylor distortion. So they are much stable and that's why they are known as static. Okay, for example, in case of CuNH3 2 plus, so this type of complex will show static John-Taylor distortion. That means you can measure at any condition. So what's about dynamic John-Taylor distortion? Dynamic John-Taylor distortions are those in some complexes no distortion can be detected at room temperature. So at room temperature you cannot differentiate between the different bond lengths. That means axial bond lengths and equatorial bond lengths you cannot differentiate at room temperature. However, the distortion can be detected by lowering the temperature. So if you change to the minus temperature, if you go to the minus temperature, so that in that freezing condition you can differentiate bond lengths of axial and equatorial in case of octahedral obviously. So that type of distortion is known as dynamic John-Taylor distortion. Okay, for example, it is observed in case of CuNO2 2 plus. This type of complex ion, it will show dynamic John-Taylor distortion. Okay, now I'll come to the previous year solve related to the John-Taylor distortion. Okay, let us see. So before going to the question answer discussion, I'll show you one chart. Here see configuration from D1 to D9 I have shown, then ground state term. So this is very important. If you remember this table, then many answer you can easily do in competitive exam in very shortcut method. Okay, so configuration D1 to D9, grounds corresponding ground state term for both high spin and low spin wherever applicable, and whether it will show John-Taylor distortion, then yes, if no, then no. So whether it will show John-Taylor distortion or not. So these three columns I have shared with you. So this will help in our question answer discussion section. Okay, that's why I just put together this table, so you can save this table for further use. So let us see first question. So which of the following state exhibit John-Taylor distortion? See, just now I have shown that table with the ground state term. So here they have given 4 ground state term, and which one exhibit John-Taylor distortion. So if you remember or if you recall that table, you see if you go with one by one with this option, see 4A2G. What is 4A2G? See, I have shown in a white dotted circle 4A2G. So it's corresponding to no JTD. So no John-Taylor distortion. That's about what's about 2T2G. That's option B, 2T2G. Okay, it shows. So it shows. Next, go to the third option, 3A2G. Where is 3A2G? D8. Okay, no JTD. And what's about 1A1G? Okay, 1A1G D6 low spin. So no. So all the three options like A, C, D, they will not show JTD. So only option B, that means 2T2G will show yes. So 2T2G is the right answer here. Okay, so this is how you can solve this type of question if you remember this ground state term of corresponding electronic configuration from D1 to D9. Okay, so let's see the next question. So if you see this question, the crystal field symbol for the ground state of MnCN6 4-. So four options are given. So Mn6 Cn6 4 minus means here Mn is the +2 oxidation state, and due to strong field ligand, that is presence of Cn minus, so it will turn to the low spin complex, formation of low spin complex. So here MnCN6 4 minus is low spin complex of Mn2 plus. So if you recall that chart, so here you can see low spin D5. Low spin D5 will have 2 T2G ground state. So 2 T2G means option A will be the right answer. Okay, so option A is the right answer here. Let us see the next question. The correct set of electronic configuration for metal ions in octahedral coordination geometry for strong Jahn-Teller distortion is. So here see there are four options given, and different pattern of T2G and EG are supplied. So you have to remember here that when EG is unsymmetrical, strong JTD, and when T2G is unsymmetrical, weak Jahn-Teller distortion, and when both are symmetrical, then no Jahn-Teller distortion. So if you see all the four options, in case of A, you can see EG T2G6 EG1, T2G3 EG1, T2G6 EG3. So in all the cases EG is unsymmetrical, so it will show strong Jahn-Teller distortion among the four options. So other will also show, but this is the strongest since all these cases EG is unsymmetrical. So option A is the right answer. Okay, so let's move to the next question. Jahn-Teller distortion is observed in an octahedral complexes with the electronic configuration of. See, four options are there, but you have to remember here this question is MSQ type, so multiple answer also applicable in this case. So MSQ, so you have to very careful. So we will see one by one what is. So you can answer this question in two different way. I have shown earlier. So you can recall that this chart, so where you go one by one. So D5 high spin, if you see high spin column, so D5, so no JTD. Now D5 low spin, so D5 low spin weak JTD. Okay, and D6 high spin, high spin also weak JTD. D6 low spin no JTD. So both D6 high spin and D5 low spin shows weak JTD. So answer will be both option B and option C. Okay, so you can do this manually also, same answer. See how manually you can do. So D5 high spin means this type of electronic configuration. So T2G symmetrical, EG symmetrical, no JTD. So D5 low spin, option B, that means D5 low spin means here see T2G unsymmetrical, EG symmetrical, so weak JTD. Now D6 high spin, so this type of configuration means T2G unsymmetrical, EG symmetrical, here also weak JTD, and in case of D6 low spin, both T2G and EG symmetrical, so no JTD. So both B and C are the correct answer, because in these two cases only weak Jahn-Teller distortions are observed. So you can use any of the method according to your convenience. I have shown both way you can do in exam. Okay, so next problem, the true statement about copper H2O whole 6 2 plus, this complex. See, four options are there. All Cu bond lengths are equal, one Cu bond length is shorter than the remaining 5, 3 Cu bond lengths are shorter than the remaining 3, 4 Cu bond lengths are shorter than the remaining 2. Let us see which one is the correct answer. So copper 2 plus, here D9 configuration, that means T2G6 EG3. If you see the structure of this complex is like that, octahedral, and we know that T2G symmetrical here, T2G6 symmetrical, EG3 means unsymmetrical, so it will show strong Jahn-Teller distortion because EG is unsymmetrically filled. So strong Jahn-Teller distortion means here it will show Z out or Z elongation. So two axial bond lengths, two axial CuO bond lengths will be longer compared to CuO bond lengths which are along the XY plane, that means equatorial position. So option D is the right answer. 4 Cu bond lengths are shorter than that of remaining 2. Okay, so let's see the next question. Which one of the following configuration will show John-Taylor distortion in an octahedral field? Here also see 4 options are there, so you can recall that chart. Here see high spin D8. High spin D8 means okay, no JTD. So high spin D4. High spin D4 means okay, it will show strong JTD. High spin D5. High spin D5 also. High spin D5 also did not show any John-Taylor distortion, and low spin D6, this is also not showing John-Taylor distortion, so only D4, so only D4 is showing, so option B is the correct answer. Okay, so in manually also you can do. So D8 high spin, both are symmetrical, so no JTD. D4 high spin, D4 high spin means T2G symmetrical, EG unsymmetrical, so it will show strong JTD. And D5 high spin, so both are symmetrical, no JTD. And D6 high spin, both are symmetrical, no JTD. So in case of D4 high spin only, so option B is the right answer. So any one method you can use according to your convenience. So next question is, for which one of the metal ions strongest John-Taylor effect is observed in an octahedral field? See, 4 metal ions are given. So let us see one by one. So titanium 3 plus D1 system, vanadium 3 plus D2 system, Mn 3 plus high spin D4 system, cobalt 3 plus D6 system. Okay, so D1 means they will show weak JTD because it is EG orbital is symmetrical, T2G unsymmetrical. D2 also T2G unsymmetrical, so weak JTD. D4 high spin means it will have EG unsymmetrical, T2G symmetrical, so strong JTD. And cobalt 3 D6 system weak JTD because here T2G is unsymmetrical. Okay, so among all these 4 options, Mn3 plus will be the right answer. So if you recall that chart also, from here also you can answer, and if you want to use that table, here also you will get answer. So if you put one by one the configuration, you will see that in case of D4, that means Mn3 plus high spin will show strong John-Taylor distortion in an octahedral field. So option C is the right answer. Okay, so next question, amongst the following, the complex ion that would show strong John-Taylor distortion is, see here they have given directly complex. So from this complex you have to write down first electronic configuration of the corresponding metal ion, then you can easily predict. Okay, so metal ions from these all 4 complexes are chromium 2 plus D4 high spin. Since here water ligand is there, so all complexes will be high spin. So chromium 2 D4 configuration high spin, titanium 3 plus D1. So D1 means high spin, low spin, both same, so no need to write down. Cobalt 2 plus D7 high spin, and iron 2 plus D6 high spin. So from here you can say that D4 chromium strong JTD because here EG orbital is unsymmetrical arrangement, and D1 weak JTD, D7 weak JTD, here also T2G orbitals are unsymmetrically filled, and T2G D6 high spin for iron 2 weak JTD, here also T2G unsymmetrical. So chromium 2 plus, that means option A will be the correct answer. So if you use that chart, there also you can see the electronic configuration corresponding to high spin D4 will show the strong John-Taylor distortion. So option A is the right answer. Next question, see John-Taylor distortion of copper 2 ion, copper dot 5H2 acts to raise symmetry, remove an electronic degeneracy, cause loss of water ligand, promote a d electron to an antibonding MO. So among these 4 options you can see here copper 2 plus will show strong John-Taylor distortion, and we know that for John-Taylor distortion they try to remove their electronic degeneracy. So option B will be the right answer. Okay, so next question, the DD absorption band of FeH2O6 2 plus is split due to presence of octahedral geometry, static John-Taylor distortion, dynamic John-Taylor distortion, and presence of trigonal bipyramidal geometry. So let us see how can we answer this type of question. So iron 2, see water ligand, so high spin complex, so D6 high spin complex, electronic configuration you can see electronic arrangement T2G4 EG2. So here T2G is asymmetrical, EG symmetrical. That means it will show weaker Jahn-Teller distortion, but when DD transition occurs, so electron transition takes place from T2G to EG. So here if you see, after electronic DD transition, T2G will have symmetric configuration and EG is getting unsymmetrical configuration, so it will show strong Jahn-Teller distortion. So it is in this case we are getting strong Jahn-Teller distortion only after the DD transition occurs. So that's why this will be the dynamic nature of the Jahn-Teller distortion. So option C is the correct answer here. That means dynamic Jahn-Teller distortion observed in case of DD absorption band of FeH2O6 2+ splitting. Okay, so option C is the correct answer. Next question, the correct statement about the Cu end bond distances in Cu NH3O6 2+. 4 options are given. So let us see how can you solve this type of question. Here see, copper 2 means D9 configuration, that means T2G6 EG3, T2G symmetrical, EG unsymmetrical. So EG unsymmetrical means it will show strong JTD. So here in this case copper, we know that Z out or Z elongation takes place. That means axial bonds are longer than that of equatorial CuN bonds. So option B is the right answer. The axial bonds are longer than the equatorial ones. Okay, so option B correct answer. Next question, the correct statement for MnO bond lengths in MnH2O6 2+ is. 4 options are given. So similarly we can answer this type of question just like previous one. Here you have to see what is the configuration of metal ion. So here Mn2+ means D5 configuration. So D5 will be high spin because water ligand is there, weaker ligand. So for D5 high spin, we know that electronic configuration is T2G3 EG2. So T2G3 EG2 both are symmetrical. So here no Jahn-Teller distortion is observed and there will be no JTD. So all bond lengths will be equal. So all bond lengths are equal in case of MnH2O6 2+. So option A is the right answer. Okay, so similar problem also comes in case of nickel also. So let us see next example. The correct statement for NiO bond lengths in NiH2O6 2+ is. Similar 4 options are there. So let us see how can you solve. So here Ni2+ D8 configuration, and D8 configuration means, see, T2G6 EG2, so both are symmetrical. So that means electronic arrangement in both T2G and EG orbitals are symmetrical. So here no Jahn-Teller distortion is observed, so all bond lengths will be equal. So option A is the right answer here. Okay, next move to the next question. So which one of the following metal ion shows Jahn-Teller distortion in an octahedral field? So this one let us see. So if you write the electronic configuration of Ni2+ high spin D8, Mn2+ high spin D5, chromium 2+ high spin D4, and cobalt 3+ low spin D6. So see, no JTD in case of nickel 2+ because here both T2G and EG orbitals are symmetrical. And in case of D5 high spin, here also both T2G and EG orbitals are symmetrically arranged. So in case of D4, so it shows strong JTD because here in case of D4, so it is EG orbital is unsymmetrically filled and T2G is symmetrically filled. So that's why strong JTD is observed in case of chromium 2+ high spin. And let us see what's about cobalt 3+. In case of cobalt 3+ D6 low spin. D6 low spin means there will be no JTD since both T2G and EG orbitals are symmetrically filled. So option C will be the correct answer, and that means chromium 2 high spin. So if you see the previous chart, here also you can say one by one, if you fill this electronic configuration, you will observe that in case of D4 high spin, there will be the no strongest Jahn-Teller distortion. So option C is the correct answer, that means chromium 2 high spin. Okay, let us see the next question. Which one of the following complex does not exhibit? See, does not exhibit negative question. So you have to remember not. sometime you can skip this. If you think it is positive question which one will show, then you will get wrong. Okay, so you will not get marks for that, but you have to remember this is negative question, which one does not exhibit Jahn-Teller distortion. So let us see. Titanium 3 plus D1, vanadium 3 plus D2, iron 2 plus D6 high spin as water as ligand here, and chromium 3 plus D3 high spin. So if you see the electronic arrangement among these four complexes, so weak Jahn-Teller distortion is observed in case of D1 because T2G is unsymmetrically filled, EG symmetrical, that's why weak JTD. In D2 same, T2G unsymmetrical, EG symmetrical, and in case of D6 high spin weak JTD because in case of D6 high spin also here T2G is unsymmetrical and EG symmetrical, and in case of D3 high spin no JTD is observed because D3 means T2G 3, that means symmetrical. Okay, for symmetrical T2G there will be no Jahn-Teller distortion. So chromium 3 plus, that means option D will be the correct answer, chromium H2O6 3 plus. If you check with that table also, you will get for D3, see D3 no JTD because if you see the last third one no JTD high spin D3. Okay, but if you compare with other D1 and D2, in case of both high spin and low spin weak JTD is observed, and high spin D6 also shows weak JTD. Only one, that is in case of D3 high spin no JTD. So option D is the correct answer here. Okay, so you can use any one of the method, you no need to worry. You also no need to confuse with both the two different method. Which one you fit with you can use in your way. Okay, I have shown both way, but you have to choose in your way which one is better for you. Okay, so this was today's discussion, and in next upcoming video I will solve the year-wise for CFSE related to CFSE calculation for IIT JAM starting from 2008 to latest 2020. You will get very soon this video, and next video on CFSE related to all CSIR, NET, GATE, SET and few sample questions I will discuss for your future upcoming exam. Okay, so thank you so much, and if you like this video, just press the like button and please share among your friends.